Hello everyone, my name is Quentin and I will present the paper Compositional Information Flow Analysis for WebAssembly Programs. First of all, what is WebAssembly? It is described as follows on their website, so it is a binary instruction format for a stack-based virtual machine. It is designed as a portable compilation target for programming languages and enables deployment on the web for client and server applications. It has been gaining in popularity these past few years, and nowadays its use extends beyond the web. But what about the security of WebAssembly applications? It states on the documentation that the design of WebAssembly promotes safe programs by eliminating dangerous features from its execution semantics. For example, if you execute a WebAssembly program in your browser, the memory of the WebAssembly program is isolated from the memory of your browser, so that if something bad happens to the WebAssembly program, nothing bad can happen to the host execution environment, which is your browser. However, there are communication mechanisms between the browser and the WebAssembly program. For example, here we have a C program that can be compiled to WebAssembly using mscripten. It uses this mscripten run script function to execute a piece of JavaScript code on the browser. The problem here is that there is a buffer overflow on this line, which diverts the control flow of the program and which will eventually call mscripten run script with this arbitrary piece of JavaScript, and that's not something that you want. So there's definitely a need for security-related analysis of WebAssembly. As a first step towards that, what we propose in this paper is a static analysis that is compositional, so it analyzes each function in isolation from each other, and for each of these functions, it computes an information flow summary. For example, one of these summaries can be the following. So this summary states that if you call a function with the summary, the return value that you get may contain information from L0, that is the first argument to the function, and L1, the second argument to the function. As is usually the case, we focus here on explicit flows, and a limitation of our approach is that we ignore memory flows. This is an unsound assumption that we make, but it didn't result in any unsound summaries in our evaluation. So our approach is the following. In the paper, we first present mini-WASM. This is a trimmed-down version of WebAssembly that we made so that it's easy to design, formalize, and present analysis for WebAssembly. We then instrumented these semantics to obtain a dynamic analysis to compute the function summaries that we want, and then we abstract the semantics to obtain our static analysis to approximate these summaries. Now let's have a look at some mini-WASM programs. So here we have a first program that first declares a type. The type is a function type from i32 to i32. Then you have a function declaration that has type 0. So 0 here means it's the first type that is declared in the program text, and this is the body of the function, which consists of instructions. Now let's suppose we call this function with argument 41. So the first thing that we do is that it creates a set of local variables. So local variable 0 refers to the value of the argument 0. So now we can execute the first instruction. We start with the empty stack, and the first instruction pushes constant 1 on the stack. Second instruction tells us that we need to look up the value of local 0 and push it on the stack. So that's what we do. Then we can add the two top values on the stack, and we get the final value, which is the return value of this function. We can also call functions in WebAssembly. So here we have a program with two declared functions, function 0 and function 1, and function 1 calls function 0. So how does it do that? It pushes arguments on the stack and then issues a call instruction, which will jump to function 0 and execute it. In the end, we'll have the result of function 0 called with 0 and 1 on the stack. So these are the concrete semantics. In the paper, we instrument them to obtain a dynamic analysis. I will not focus on that here, but the idea is really to have a dynamic analysis that can give us from the execution of a WebAssembly program, it gives us a set of summaries that have been produced. What I will describe now is the abstract semantics, so basically our static analysis. So the abstract semantics are focused on analyzing one function in isolation from the rest. So here we have two functions, and an important aspect of it is that we completely ignore everything about values in the analysis. So we don't care about the values of, we don't care about the values, but we rather care about which information they may contain. So here the local values are represented by these names. L0 means that this value actually contains information from the argument 0 to that function. Same for L1. So if we analyze this program, we get the first local. So on the stack, we know that the top of the stack may contain information from the argument, the first argument to the function. We can do the same for the second instruction. And then as we add the values together, we have to join these abstract values. So the value that is on the top of the stack is L0, L1. That means that this value in a concrete execution may contain information from both arguments of the function. The summary of this function is this final value. It may also contain other information about global variables, for example, but we will only focus on the return value of the function here. So what this summary means is that if you call this function, the return value you get may contain information from both its arguments. Now let's analyze the other function. So we push constant 1 on the stack because we don't care about values, and 1 doesn't contain anything about any information about the arguments of the function. We represent this by the bottom symbol. Then we access the first local and we call the other function. However, because we analyze functions in isolation, we are not actually calling it, but rather we will use its summary to deduce the information after the call. So the summary of function 0 was this one, and we call the function with bottom and L0. So what can we do? Well, we actually apply the summary by replacing its arguments by the values that we have, the abstract values. So we replace L0 by bottom and L1 by L0, which gives us L0. The final abstract value for this analysis is L0. So the summary of function 1 is L0. That basically means that if you call function 1, the return value you get may contain information from its first argument. So all of the details about the abstract semantics are in the paper, and I will now focus on the analysis process. So given a WebAssembly file, what we do is that we parse it, we extract all of the functions, and then we extract an approximative call graph. So here we have, for example, function 1 that calls function 0 and function 0 calls function 2. This call graph is approximative because on top of the call instructions, which precisely characterize the target function that is called, we also have indirect calls in WebAssembly. Indirect calls, for example, are used to encode function pointers. But fortunately, WebAssembly provides us with some information to restrict these possible targets. For example, there is some type information for indirect calls. So given this call graph, we can compute an analysis schedule. So because, for example, function 0 calls function 2, we need to produce a summary of function 2 so that it's available when analyzing function 0. So that's why you need to analyze 2 before analyzing 1, before analyzing 0 before analyzing 1. 3 and 4 are mutually recursive, so we need to analyze them at the same time. So these sets are basically strongly connected components of the call graph, and they need to be analyzed one at a time. Then we can analyze each strongly connected component. We can start with 2, followed by 0. So these produce some summaries, followed by 1. And then we can analyze 3 and 4 at the same time. It may require a few iterations to stabilize the analysis, but it will eventually terminate and provide us with a set of summaries. So we have implemented this analysis in OCaml. It supports most of the WebAssembly standard. And we have also instrumented the interpreter that is provided with the specification of WebAssembly to obtain the dynamic analysis that we were talking of. All of our implementation is available online for free, and we have evaluated it as follows. So our method was the following. Given a WebAssembly program, we run it with the instrumented interpreter, basically our dynamic analysis, to produce a set of concrete summaries. We also analyze it with our static analysis to produce abstract summaries, and then we can compare the abstract summaries to the concrete summaries. If they match, that's all good. If, however, the abstract summaries contain more information than the concrete summaries, it means that they may be imprecise, so they are marked as a potential imprecision in the analysis. We have performed this evaluation on 34 C programs that each have been compiled to WebAssembly. In total, that makes almost 200,000 lines of WebAssembly code to analyze, which have been analyzed in less than a minute for a total precision of 64% on the summaries. This is in line with related work on taint analysis. So to recap, I have proposed compositional information flow analysis for WebAssembly. So this is the first compositional analysis for WebAssembly. In the paper, we detail how to correctly approximate indirect function calls for the analysis of WebAssembly program. Our approach was to first present mini-WASM semantics, instrument them, and then finally abstract them to obtain our static analysis. Our implementation is available online, and we have evaluated it on almost 200,000 lines of WebAssembly codes. As future work, we leave memory flows, which are an unsound assumption that we make in this work, but we would like to continue working on that. So to wrap up this presentation, I'll leave you with two questions. The first one is, should new languages be designed in a way so that they can easily be analyzed? In the case of WebAssembly, for example, when you have indirect function calls, type information helped us a lot. And so that's something that's good. Is it something that we want in more languages? That's a question that I leave for you. And the second question is, should researchers forget about the soundness requirement of the analysis that they propose? This is basically what is proposed by the soundness manifesto and is something that we do here with the memory flows. So thank you for your attention, and we'll be happy to answer any of your questions.